I don't have any slides for the spreadsheet. It will be on the website, Iowa DOT Bridge website, tomorrow morning, I hope. If you get those electronic updates from the DOT, they come out the first of the month. And it should hopefully say something about it being on the site. And it won't be on Google's site, but this is the fastest way I know how to get to the bridge site, if I can spell. So if you're looking for it and you want to use it or try it out, play around with it, we'll let that clear up. Loading too much information, I think. I got to use my box. That's why I brought my box. All right. Plus I have your PDHs up here, which I will eventually put under that monitor over by that door. And when you leave, your visitor passes can get thrown in the box here, so you don't have to return those. All right, now I don't have to bend over. So we're on the Iowa DOT Bridge site under Automation Tools, under Final Design Software. We got a bunch of different programs. It's not going to let me scroll. It's probably going to appear under the Iowa DOT Substructure Applications somewhere under here as an Excel spreadsheet. Probably be called something like LRFD Pure Geo or Pile Geotech Design. So you'll see it there. Now, just back to the spreadsheet. On all the spreadsheets we put out, we usually put in this disclaimer. At your discretion, you're responsible for using it properly, correctly, and if there are errors in it, it's up to you to find them. Of course, you can let me know if you find them so I can correct it. That's always appreciated. But our designers have been using it a little bit in-house already, and I've made a couple changes since it first came out. Last one just a couple days ago. So hopefully it's got most of it in there correctly. So you have that typical disclaimer, and down below there's a little bit about the description of the various tabs down along the bottom there as far as what's happening where. And then just to point out, I don't know how well the color is here, but anything that's a blue cell is usually something where you have to provide input, and a red or orangish type of cell is where a calculation's happening automatically. And then down here, I usually, if I make updates that are substantial, I'll probably add in what I did just to keep a record. I'm going to jump past these three tabs for a minute. This is where the main work is going to go on. And I'm going to just jump over that to show you, I've got the friction chart in here. I've also put in the soil classification next to that for the cohesive, non-cohesive classifications. We put the end bearing chart in here. I got a few notes that's out of that volume 4 about the generalized soil category. So that's covered. I got all the resistance factor tables in here as well. So you don't necessarily have to jump to the bridge manual. Now the bridge manual will be have the final say on policy. So if there's a contradiction, bridge manual controls, you know how that works for plans, right? Was it special provision controls over the plan controls over, and so on and so forth. Same thing, bridge manual always controls, and Ken Dunker controls over that. So, so if you call him, you get the latest. There's also a table, we make some recommendations about if you're getting down to rock, how far into the rock should you go. So there's some rough estimates. So it's a little bit at the discretion of the designer as far as how much more pile length they want to add on if you're going to rock. So jumping back, what I did is I did track 1, example 1. So I don't know if you need to or not, you've probably seen it so much today, you got all the numbers memorized, but it's topic 7. I'll be just briefly going through that. I'm not going to do tremendous detail. You've already gone through some of the calcs. I'll just show you a little bit how this is supposed to work. In Excel, if you have a little red triangle in the corner, it tells you a little bit more information as you hover over each cell. So you can get a little additional there. For instance, bridge description is just a general thing that you might want to have in there, which bridge are you working on. This is actually, the abutment or pier is actually used in the plan notes on this second tab here. So some of this will show up directly in the plan note because I'm generating those inside the Excel spreadsheet for use. The scale here is a little out because I'm zoomed in about 80%, so some of this is getting truncated off. If it's at 100%, I think it'd probably show up fine. But boring numbers, just for information. You know, sometimes you might be iterating or interpolating between borings, so maybe you want to add 1 or 2 there, just for reference to whatever particular pile bent you're working on. Natural ground, the only thing I'm really using that for is, you know, where if you're in a glacial clay, if you're 30 feet below natural ground, you get to use a higher or lower value depending if you're above or below. So I use that, subtract 30 feet, and so it kind of tells you maybe I should put a layer at 410 because I get to use a better value below that. The key question didn't really come up today. Where do we have 440 elevation in Iowa? I'm used to seeing 900 or 1,000 or something, so maybe we're working in Pennsylvania. So anyways, it's all reference, so it doesn't matter. Water table, just for information, it's not used anywhere. You saw it maybe mentioned today, but we don't actually use water table to change anything in how we do the design. And perhaps we should on sands, but we don't. Bottom of cap for that particular track one, example one was 433. I got kind of an extensive note here. Part of the reason for that is, of course, on an integral abutment, the bottom of cap is at the bottom of the abutment. On a footing for a T-pier or frame pier, it's at the bottom of the footing. But if you have a pile bent that's individually encased or fully encased, you got to think a little bit more about how to use the spreadsheet anyway, because you might set bottom of cap at the bottom of the top, or you might set it at the bottom of the encasement. And this came up on a project a little bit where we were going to do these test piles, which actually won't get driven until spring, but we were talking with Office of Construction, and I guess they do it different ways, the contractors do on a pile bent. This was a fully encased one. I guess sometimes they'll drive the pile first and then excavate the soil from around the pile. I would have thought the more common way would be excavate the soil. First you excavate the soil, then you drive the pile, rather than drive the pile and then excavate the soil, because getting the soil out between the piles seems like a pain, but I guess they do it both ways. So you have to realize you're going to get more driving resistance if you're leaving the soil there and you're going to dig it out later. Now most of the time the soil on the top, as Ken mentioned, is junk, so it's probably not going to matter too much, but in this case we were doing fairly deep encasements, and it was pretty good soil, so it made a pretty big difference in terms of what we should put down for that, what we used to call theoretical driving resistance, and now we're calling target nominal driving resistance. So just be aware of that. As far as construction control, I kind of added modified Iowa DOT and formula later. The state pretty much, only uses WEEP, and so for the conference I added this in. It doesn't really control much of what you're going to see down through here. I left it pretty open in terms of which way you go. This, once again, is just mostly used for the note, for that last part of the note that says, WEEP's the construction control, or the Iowa DOT formula is. So that's all it's really doing right now. All right, so you can handle in the spreadsheet, you can handle scour. You would say, yes, I have scour, and my scour is down to this elevation for the 100-year flood from the hydraulic data. You can also add pre-bore, which for a lot of our bridges is 10 or 15 feet at integral abutments. You might try to go a little farther if you have down drag, of course, because you're trying to get through those layers to get as little down drag as you can. But there are limits to how far you should do that, because you might buckle your piles, of course. So there's recommendations for that in the bridge manual. So once you get through these upper layers of input in the blue cells, you'll jump down here, put the bottom of boring elevation. I use this basically if your pile ends up being longer than your boring, you can decide whether you're worried or not. At the DOT, we found out sometimes people go 20 feet, their pile's 20 feet below the bottom of the boring. And you go, well, you might hit rock first. It's probably good soil, at least as good as the stuff you've seen, and probably better. Are you going to go and do more borings? Probably not on your typical bridge. So we have talked to the soils office, and hopefully we'll get a little better correspondence or how deep the boring should go in the future. So that's kind of one issue there. So the program will flag you if your pile ends up going below your boring, just to let you know. This thing does not want to roll. My mouse roller's not working here. All right, so you come in here, we're track 1, example 1. You enter your starting elevation of your layers, 440. You type this stuff in. This is calculated because it's red. So you put in your soft silty clay. It's a cohesive layer. You put in a C for that. It's described up a little there if you want to see that. R is for rock, if you got rock. If you're going down to rock. D is for down drag. So all the layers, the compressible layer, that gets a D, and all the layers above get a D, right? Because they're all going to settle and drag on your pile. That's talked about here as well. You put in your average ends for however you want to break up the data you get from the geotech guys. If you want to split it up into up to 20 layers, I guess you can do that. My guess is you'll get away with 4 or 5 or 6. Nominal friction resistance, that's where you go to the chart in the blue book, grab those values, plug them in. If you have end bearing, you can put in multiple values of end bearing. The sheet will figure out how far the pile has to go, and if you have end bearing on every layer, wherever it needs to stop, it'll use the end bearing in that layer where it stopped. In this case, we didn't have any end bearing. I'll add this too as I go down here. Pile design in the past, we joked about a little bit at work. You always kind of do it on a napkin or a back of an envelope, right, because it was so easy. It's still pretty much that way as long as you don't deal with setup. Otherwise, the only difference really is you have a little different blue book values, a little different phi factors for mixed and non-cohesive. But if you throw setup in there, it gets a little more involved. So that's why we wrote this. We had a spreadsheet in-house for the old ASD, but I don't think anybody hardly ever used it because you just write it down quick and you'd be done. So hopefully this keeps that process a little faster. So you come down here, you add your pile. Once again, it's more for information because you're grabbing your blue book values. This is not feeding them in there. You're actually entering them yourself from the table. So this is more just for information. Pile areas for information because up above here, you're putting the nominal end bearing resistance in kips. You're not tying it to the area of the pile. So once again, it's just information. Pile cutoff is used. Once again, it's the zoom scale that's, I think, screwing this up. But I give you the basic cutoff piles that the cutoff we use for the different pile types. I give you the embedments we use on our different types of footings, whether integral, stub, or frame, whatever. I give you the increments we usually round to for the different types of piles. You can enter all that in, and that's all used in determining the contract length. You put in the factored axial load like we've been talking, a nice little equation, the gamma Q. Throw that in 128 kips in this case. Now, since we assumed in this example it was going to be a cohesive soil, and so we're going to grab, we can see the factors up here, and I will explain this. What I decided is this spreadsheet's not going to do any track 3 type design because I don't think anybody's going to use it very much. So you're on your own if you have to do that. This is more for the track 1, track 2, and in the track 1 in particular, it's a weep only. I don't put the values in for the PDA, CAPWAP kind of stuff. Once again, that's not common. So I'm just going to give you the values here so you don't have to go look them up. They'll be right there for the different soil types. And in this case, it was cohesive. We're doing a weep only, so it's 0.65. And if we had end bearing that was not rock, we could also use 0.65 on the end bearing. If we have rock, for bedrock, I list the 0.7 here, so you would put that in there if you were going down to rock. I've got the load factor for down drag, which is 1. I'm going to zoom down a little more. All right, so up to this point, all you've been doing is putting in all the givens, all the knowns. And now you're going to let the spreadsheet figure out how long your pile should be. And I already ran it, so the values are in here. I'm just going to delete a bunch of stuff, and hopefully this will work, right? So the first thing you kind of do is you want to estimate your contract pile length. You're in your design phase. Those were your design resistance factors. And all you do, this says VBA code behind it. It's not purely formulas. Some of these are formulas that are set inside Excel and they don't change. But I also have VBA code here, so this is a button. And you just push the button. And it says it's 75 feet, which I believe matches what we've talked about today, hopefully. If it doesn't, this is right. It rounds to the nearest. We decided we're going to round to the nearest, which most people round up, but we're already getting longer anyway, so why round up all the time? And then what it'll do is it'll go through, it'll start with the bottom of cap elevation, always on this line where you start, and of course there's no capacity there. It'll always put in this line. If you had pre-bore, it would show something to show that you had the pre-bore, and it would show the different elevations, or scour, because we don't want to count on the scourable material in the design because it's not going to be there to count on necessarily. So it'll show that as no resistance 2 if there were any. And then it starts with the layers. Now if there were scour, maybe it would skip layer 1 and 2 and be down in 3, so it would skip over those if that was needed. But otherwise, we have no scour, we have no pre-bore, so layer 1 it's going to start with, and it'll start figuring out the capacities and the lengths in those layers. It'll refeed these, what you entered for cohesive, non-cohesive. It'll redo the average blow counts. It tells you what the length is, and you can see obviously we're ending in the last layer over here because that's 49.66 feet. You can see the factored friction resistance. This is a little different than the examples we were doing. We did a lot of stuff today in nominal resistance, right? The reason I jumped to factored, so let me scroll up just a little bit, is because of this. If you had rock, then you would have 2 different resistance factors, and so working in nominal isn't as intuitive because you've got to split out your capacities to the end bearing, to the friction with different resistance factors, and then it's just not as intuitive. So if you work with the factored stuff, then you know that whatever you put up in the soil chart way above got multiplied by this resistance factor to reduce it down. As I show here, this is the kips per foot, so it's reduced down from whatever was above, in this case only by 0.65. But if you had end bearing and rock, it would reduce it by the 0.7, or whatever you put in there. And then so it does also figure that out, and it does the kips per foot, shows you what it was using, and then it's the 0.52 times 6 feet should be 3.12 kips. That's what you got in that layer, and it keeps track cumulatively of what's going on. And then you get to the 128 kips, and because this is factored now and not nominal, you can compare it directly to the factored load from the structural guys who figured that out. All right, so it does that. Let's scroll down just a little more. So I've only pushed this first button so far. So my cumulative pile length, if I add all these up, it's going to be 72.66. And what I've done in this spreadsheet is, you saw I deleted a bunch of stuff. Well, there's a formula here. So I deleted a formula, but what I do in some of the VBA code is I actually write the formula in the cell so that if you want to know where did this number come from, You can track it. You know, it came from F54 and K25, so you know where it came from. Now that'll get overwritten anytime you push the button, but that's the intent. So you don't just say, well, where'd that number come from? You can at least find out where else in the spreadsheet it was used. If there were factored down drag load, that would be here. We only have the factored axial load of 128 kips, so this plus this is still, the total is 128, and the total factored pile resistance matches it exactly. We got exactly 128 kips because the spreadsheet iterates and interpolates and does all that better than we do, and so it comes out perfect at 72.66. Well, then you start first checking, okay, am I actually cohesive like I assumed? It figures that out for you, and it says you got 87.6% cohesive, so definitely this is a cohesive pile or a cohesive soil category. And if it wasn't, you would have to go back, look at what you put in for your resistance factors up above and change them if it came out different. And hopefully you don't get in that endless loop thing, right? We haven't had it happen yet, but you could. You could say, well, I'm going to go to non-cohesive, and suddenly it comes out cohesive. You say, well, I'm going to make it cohesive, it comes out non-cohesive. So go conservative if that happens. You probably go non-cohesive then. So you've done that. You know it's cohesive. Then it starts doing the rounding for you. It adds in the 1 foot for the cutoff, the 2 feet into the integral abutment embedment. Talks about it here. It's 75 feet. So that's your contract length. Now I do figure out the nominal resistance down here. So if you had rock, it takes all that into account, splits it out, and gives you the nominal resistance to work with, particularly as you go into the construction stage. But anyways, once you have this estimated pile contract length, I tend to recommend you come over here, you put that value in that you really want to be the contract length, put it in here, and press this button and calculate the factored pile resistance based on that length. Because now it's going to be just a little bit low, like the warning says, because it's taking that 1 foot of cutoff off, it's taking that 2 feet in the abutment off, and so your pile is a little bit shorter than when you push the other button. So you're slightly below the 128, and the warning tells you that you're, 1,380 pounds below. Big deal. But if you were way off, this would let you know. Some of the other warnings, if your pile tips within 5 feet of a layer, it'll tell you. You can take that however you want. The idea is if you're really close to a boundary layer, you may want to extend your pile through it a little farther to make sure you get the capacity you think you're getting. So it just tells you that's the case. It doesn't, it's a warning. It is possible you could have screwed up your entryway up top when you were putting in values up here. It's like, well, you got to your last layer, you forgot to put in the friction resistance, and you put in 10 kips of end bearing. Your pile may never reach capacity, so it can't actually solve the problem, right? Because 10 kips of end bearing won't get you what you need without any friction. So there's that kind of a warning. As I mentioned, there's this warning where you might be a little under, and the last one is, as I mentioned, if you're below the bottom of the boring, it'll tell you. All right, so moving on, we've done this. Push it again just to make sure. So we're done the design stage. We've got our 75-foot contract length. We know our nominal resistance. Now we're going to move on into the target nominal pile driving resistance stage, the construction stage. I've got a few extra notes up here you can read if you want. But it'll pull some of the values from above, re-put them down here just sort of as a starting point. I've got that other chart, just the values. I'm the WEEP only track 1, the track 2 Iowa E&R just for the construction control. So there's the setup kind of stuff going on. You specify whether you want setup, which would only be for WEEP. Then you put in the 0.65, the 0.2. You say, will the pile tip out in bedrock? Yes or no. One quick thing I want to mention up here, I better mention. I have a note somewhere. Okay, if you do an estimate pile contract length and you have rock, it's not going to add on that recommended extra 5 or 8 or 10 feet because it's going to hit that rock. It says, you got capacity, I'm done. That's partly why I put this in here, because if you hit the rock, you want to probably put that in as you move on down. So let's say you hit, I don't know, some good rock, and you want to add your 10 feet, so you put in 85 feet instead of what got figured over here, and that'll show up in your note. So there, I do note that here. You just got to be aware of it as you're using this. All right, so we were down here. We're going to cohesive soil. We're going to do the setup. We don't have any scour going on or pile length subject to scour. I guess that gets calculated down here, so I won't worry about that, because you have that, maybe you have that extra driving resistance you got to have as you go through those scourable layers that you couldn't count on in design. I put my fee factors in, so I'm ready to push the third button. There's only 3 buttons. So I pushed the button. It jumped a little down below my table. It refigures this kind of stuff. So if you had those extra layers to drive through, it'd be figuring that capacity for you. Once again, it checks, is it cohesive or not? In this case, it is. It figures out the average N for you. So it looks at the ends, looks at the pile going through those cohesive layers, calculates it. It calculates the F setups for you for 1 day, 3 day, 7 day. And the way it does that is that's the nice formula that generates this graph. I've plotted out all the values based on the constants that go in this formula for an N of 1 all the way to, I think, 50 or something. And then it plots the graph. But I figure out the F setup using this formula in here, so it's more exact than you can do on the graph, right? So there it is. Then what it does is it gets you that target resistance factor, right, based on the 0.65 plus 0.2 times the F setup on a 7-day. And there's a formula I generate that does that. So that's 0.77, and it gives you that target driving resistance based on the various information you've entered so far using that 0.77. And then it uses those setup factors multiplied by that to give you these various target things, retap values, and then it calculates that minimum retap we talked about, where there's no reason. I mean, you might get 266 kips, but obviously your designer's conservative. He's only taking like 20% of the setup, so we're not really counting on that full 1.61. We're kind of scaling back and saying, well, since we're being conservative, we only have to get this, so why go for this when we know we only need that? And that comes up in the notes that are generated. And that's all there is on this sheet. And then you jump to the plan notes. What happens is it takes all the information on that other sheet, generates the notes for you. So you got the contract length, 75 feet, west abutment piles, it's cohesive. There's your factored axial load, 128 kips. You got your geotechnical resistance factor of 0.65. I don't calculate this minimum tension force, kind of a deal. If your pile length's dependent on tension for some reason due to uplift, you'd have to include that on your own. So then the next part of the note is, the construction control fee factor was 0.77 for cohesive soil, and then down to what the contractor wants to know. I got to hit 83 tons for the west abutment piles at the end of drive to achieve bearing. If I don't, I got to get 98 tons. I didn't put in the 1 day, 3 day, 7 day because he's got to hit 98 tons. That's what's controlling. It doesn't matter what day he's trying to get that. He's got to get it if he doesn't get end of drive. And unless the piles reach refusal, so on and so forth. And if you want to know where these notes come from, you scroll down, and I got a bunch of note fragments with if statements all over the place. And it slaps these together to form the notes. So those can hopefully go on the plans. You might have to edit a part out, something like this minimum embedment, whether you use it or not, depends on your particular case. And then finally, there's a graph that's generated just to give you a little visual. This first upper line is a natural ground line. You've got the pile outline. If you had pre-bore, that would show up around here. This would be the pile cap. Your various water tables shows up to the 20 layers possible. And your bottom of boring shows up down here. And so it's just sort of a visual to make sure you kind of were doing what you thought you were doing. And that's the spreadsheet. Like I said, it'll be available on the website hopefully tomorrow morning. And I'm sure it'll undergo revision. Everything I do goes under revision once people start using it. So.